Hello students, in this video we are going to learn the formulation of linear programming problems. For this video I have referred the book on Introduction to Operations Research by Hira and Gupta. Now as the name indicates, we are going to learn the linear programming problems so the linear functions are being involved into that. Now in this linear programming problem, we have to either maximize or minimize the objective function. The objectives are maybe the profit, cost, production capacity and other measures of effectiveness. So we can maximize the profit, we can maximize the production capacity, whereas we can minimize the cost or other measures of effectiveness as per our requirement. So the linear programming problem are divided into two parts. One is the objective function and another part is the constraint equations. Now in the objective function, it is represented as z equal to, it's a function of x, that is a variable, and the constraint equations can be 1, 2 or many. Now here you can see that on the left hand side of these constraint equations, it is given as a1x1 plus b1x2 plus and so on. It can go up to even bn xn also, depending upon the number of constraints. Then there is an inequality sign. It is less than or equal to, greater than or equal to, or equal to. It's equal to a constant c1, c2, c3 and so on. So these constraint equations, that is what we have to define. What are the constraints now? The constraints are the equipment, the number of equipments, or the time of the equipment, the area, storage capacity, raw materials, it may be the quantity of the raw materials, labors, working hours. So these are the constraints. With this constraint, we have to maximize or minimize the objective. Now let us start with one or two examples. Let us formulate these problems. LPP is a short form of the linear programming problem. So the requirements of LPP are the well-defined objective function, the constraint equations as linear equations in terms of variables. There should be some alternative production process. So that is how the constraint equations will be coming. Then the decision variables are non-negative, and the very important lastly, that is the resources should have limited supply. So now with this example, let's formulate the LPP. A firm produces 3 products. These products are processed on 3 different machines. The time required to manufacture 1 unit of each of the 3 products and the daily capacity of the 3 machines are given as below. So in this table it is all given, the machine capacity, time per unit for the manufacturing, and the profit is also given for the 3 products 1, 2 and 3. So now we have to find out, we have to formulate the LPP. So now let us see what are the constraint equations and what are the objective function. Now here it is given that the profit per unit of the product is 50, 70 and 80. So it is very obvious that we have to maximize the profit. So here we will be going for the maximization problem. So with this we are going to maximize. We have got the profit per unit for the products 1, 2 and 3. The constraints are given as the machine capacity. The machine capacity for each machine is given as M1, M2, M3, that is 440, 470 and 430. It is given in minutes per day, and the time required for each product for various machines are also given. So these will be considered as the constraint equations, the constraints, and the objective is to maximize the profit. Now let us, so with this identification of the constraints and the objectives, we will be able to find out, or we will be able to then define these equations. So now here we will be giving these products as here the product x1, product 1 x1 will be manufactured, product 2 x2 will be manufactured, and for product 3 let us say that x3 will be manufactured, number of minutes. So now here 2 minutes for m1 is required for x1, 3 minutes for x2, that is the product 2 are required, and for product 3 2 minutes are required, whereas the machine capacity is given as 440. So here I can write it down as 2x1 plus 3x2 plus again 2x3. The capacity is given as 440, that means our inequality sign has to be less than or equal to. Similarly for m2 it will be 4x1. Now there is no product 2 for m2, so it is 0, it doesn't come into picture, and for product 3 it is 3x3. Again, as the capacity is given, it is less than or equal to, and same as for the third one m3 it will be 2x1 plus 5x2, it should be less than or equal to 430. Now the x1, x2 and x3, these have to be greater than or equal to 0, because these are the number of the manufacturing units. So you cannot manufacture negative units. So this is how the problem statement will be. So the objective function is given as 50x1 plus 70x2 plus 80x3 is the z, and these are the three constraint equations with non-negativity conditions as x1, x2 and x3 greater than or equal to 0. Now let us take another example. Now here it is a similar example where there are 4 food types are given, and the yield per unit are given as proteins, fats and carbohydrates. The cost is given. Now because here now the cost is involved, we have to minimize. This is the problem of minimization, right? And then if we give the food type as, for the first one it is x1, x2, x3 and x4, here it will be, so the your constraint your objective function will be minimization of the cost, that will be equal to, if we 45x1 plus 40x2 plus 85x3 plus 65x4, and the constraints are, for each food type which is manufactured, there are 3 units of proteins, 2 units of fats, 6 units of carbohydrates for x1, 4 units for of proteins, 2 units of fats, 4 units of carbohydrates for x2, and so on. And its minimum requirement is given as 800, 200, 700 and so on. So it will be here. So total for this all the food type, the protein requirement, minimum requirement is as given as 800. So it will be 3x1 plus 4x2 plus 8x3 plus 6x4. It should be, minimum is given as 800, so it has to be greater than or equal to, the sign has to be greater than or equal to. Similarly you can do for fats and carbohydrates. So it will be 2x1 plus 2x2 plus 7x3 plus 5x4. Again it should be greater than or equal to 200, and for carbohydrates it is 6x1 plus 4x2 plus 7x3 plus 4x4. Again its capacity, that is the requirement, has to be greater than or equal to 700, and again our non-negativity condition will be there existing. So x1, x2, x3, x4, it has to be greater than or equal to 0 always. So now again here the same thing has been explained. So we have to minimize the cost, so that is a minimization problem, and the constraint equations are given. So our final linear programming problem will be to minimize z equal to 45x1 plus 40x2 plus 85x3 plus 65x4, which is the cost, and these are the constraint equations. Similarly the other problems also you can solve. So this is another problem. A firm produces an alloy having the following specifications. The properties of the raw materials are given, and whatever the requirements are given over here on the left hand side, and the cost for the raw materials are given in tons. Now here you remember that the cost of various raw materials per ton are given like this. So it is 90 for A, 280 for B and 40 for C. So similar to the first two examples, we can formulate the problem. This is the explanation for the formulation of the LPP. The cost is minimization, so objective are to minimize the cost, and here the specific gravity, its requirement, chromium, the constraint, and the melting point, its constraint are being identified. So our equation will be this one. Okay, the objective function is given to minimize z equal to 90x1 plus 2a2x2 plus 40x3 and other constant equations. Now if you see the last one, it is x1 plus x2 plus x3 equal to 100, because in the example only it is given as the cost per ton. That means the value of x1, x2 and x3, it should be equal to 100. The sum of x1, x2, x3 should be equal to 100, and other our non-negativity condition, it will be as it is. Again we will take another example. Now this is the advertising problem. So there are 4 different types of advertising media. The cost of each advertising unit is given, and the number of potential customers that can be reached by each one are being also given. So now the constraint, so with this what we have to do is we have to reach to the maximum number of people, right? So we have to maximize it, and the company does not spend more than rupees 4,50,000 on advertising. So the total cost of these media and this advertising is 4.5 lakhs, and for that these are the 4 different conditions which we have to satisfy. So we will see that again here, if you go through this example critically, you will see that this is the formulation of the problem, where the objective is to maximize the number of customers, potential customers, and with the constraint equations given as, so there will be actually 6 different conditions, constraint conditions which are there. The last one, it has to be x1, x2, x3, x4. It should be greater than or equal to 0. That sign is missing. So this is how you can formulate the linear programming problem.